Welcome to the structure analysis class. In this class, we'll discuss about the moment diagram and construction using the method of superposition. So what is method of superposition? So before going into the exact method of superposition, let's quickly review a few bending moment diagrams which will be useful for us to compute. So for example, this is a first beam we'll consider. So this is a cantilever beam, right? Once one side is fixed, another side is free. So what will be its bending moment diagram or bending moment shape? So bending moment shape will be something like this triangular shape. So I'll just quickly solve these parameters. Mm, yeah. So here it is given that P is acting and total L is distance is L. So what will be the moment at this point? Moment will be simply moment at A will be considered this is at A. So moment will be P. P is force acting at here into P into L, right? P into L is the total distance, which is negative because it is acting as a clockwise. So that's what the moment diagram. So moment diagram at this point, at this point, it will be minus PL. That's what we have just computed, PL. And at this at x equal to 0 at the starting point, it is 0. So just to draw it, it is a triangular shape. So this is the first moment diagram. Very simple, cantilever and the point load is acting at the tip. So in that case, this is the moment diagram. So next is the same cantilever beam. Now the load is now UDL. Now can you draw the moment diagram? So our procedure will be same. So what will be the procedure? So just W not is acting. Just consider it a distance of x. We are just deriving. Then what will be happening? So at a distance of x, if you take a section, then how much will be the moment? So if you take a section here, and what will be the moment? Moment will be Wx into W naught into L, right? Is the force. So if you take a moment, so mx at a distance of x, we are just computing at a distance of x from this side, right? From this corner, we have at a distance, and mx will be what is the total load? So UDL is acting W naught. So total force will be W naught into x, and distance will be x by 2, right? So if you just replace it into a UDL, I mean concentrated load, it will be W naught x, and this distance will be x by 2, right? So W naught into x by 2, so we will have W naught x square by 2. So similarly, if you have just replace x with L and tail length, then you have the WL square by 2. So that is the moment at this point, and moment at this tip here, tip it will be 0. And what is the equation? Just now we derive W not x square by L, right? So this is a parabolic equation. So this is the equation of a parabola. So that's why this is a parabolic shape. So this diagram is a parabolic shape, and this is a moment diagram for UDL cantilever if a UDL is acting on a cantilever. Very simple thing. Now if you see this figure, so this is the cantilever beam, and only a single moment is acting at the end. Moment m naught is acting. So what will be the moment diagram then? So this m naught will be constant throughout the length. So it is m naught is constant. So this is simple moment diagram. It is a rectangular block. And now if you have a cantilever beam where the UVL, uniformly varying load, is applied, then you can just solve it and you can find it out. This is a moment diagram. So just let me do it quickly. So what will be the total force acting because of this? So total force acting because of this will be simply area. We already discussed all these things. So area under this curve. So how much will be the area? Area will be half into base. So base is how much? Base is L into height is W naught. So that much is the total force acting, right? Total force acting. So if you just this forces, if you replace this UVL into a single concentrated load, and the magnitude is this much, right? And what will be this length? So this length will be L by 3, right? Centroid of the CG. So what will be the moment here acting then? Moment will be force is half into half L into W naught into distance. Distance is L by 3. So LL will be cancelled out. So what you have is, uh, sorry. it is W by 2, na? Sorry, I'm just missed it. So it is total load is actually half into W naught into L, right? This is the area, that is the concentrated load acting, and at a distance of L by 3. So how much it will be? So W naught L square by 6 minus. So that much moment will be acting in this point. So that's what we have written, W L square by 6. And this equation, this is L cube, right? W L square by 6. So this is a cubic curve which will be acting here. So this is the equation for if in a cantilever, if a uniformly varying load is acting, then this is a bending moment diagram. So these few bending moment diagrams are very important, because in next slide we'll discuss all these things, the application of this each bending moment. So let's solve this problem. So this is a beam. This is a simply supported beam, having one end is hinge, another hand is roller, and UDL is acting 4 kN per feet, acting at up to distance of 10 feet, and then you have a concentrated load of 30 k-feet. This is concentrated moment is given. So this is a simply supported beam having two types of loads. One is UDL acting at up to 10 feet, and then you have a concentrated moment 30, which is acting at 10 feet again. And you are asked to draw the bending moment diagram for this beam. So if we use our normal method of calculating, that is using the bending moment function, so then it will be a little bit tricky, because you have here two types of load. So basically we have to divide two times, you have to do it, so it will be a little bit tricky to do that in our normal method. So here in this lesson, basically we are learning how you can use the principle of superposition to find out the bending moment diagram. So using principle of superposition, basically you can easily or quickly, I would say, you can find it out the moment diagram for this beam. So how to do that? So in a principle of superposition, first actually we have to divide this beam into a number of multiple simpler frames, simpler beams, and each beam also should be in a statically determinate shape, or should be stable. So here we can convert this simply supported beam into this beam, where we make this end. Originally this end was a hinge end, right? A is a hinge end. But in our hypothetical beam, what we made is this end we made it as a fixed end, and then you have the UDL same, and then you have 300 is acting, and here although it is a reaction force 25k is acting upward, but in our hypothetical beam we considered it as a force acting 25k upward. So this is our hypothetical beam. What we did is we essentially changed here, and in this fixed end we made hinge end into a fixed end. That is the only change we have made. So now this is the beam. Now, so now this beam can be divided into three parts. What is three parts? First one is we removed this 25k load, and as well as this moment also. So this is a simply cantilever beam having a UDL. So this is our first part. So this beam is actually divided into three parts. So first is this is a UDL. This is a fixed beam, and only UDL is acting. So this is first part. Now second part is this is a UDL, I mean this is a cantilever, and only moment is acting at this location 300, only moment. And in the last part, this is a cantilever beam, and we added only this load 25k load is added here. So essentially these three, if you add it, you will get the original this beam, right? This is a cantilever beam with three forces are acting, right? This is UDL, moment, and load, concentrated load. So these three actually we divided into three parts. So it's simply beam, cantilever beam with UDL, simply cantilever beam with a moment, and simply cantilever beam with a point load. So now for these three individual beams, we will draw the bending moment diagram. So this is our original complex beam. What we did is we essentially we divided into three simple beams, simple cantilever beams. And then now we will do it for each moment. We'll draw the moment diagram for each of the beams, and then we'll just superimpose using the method of superimpose. If you remember, we discussed the principle of superposition. So using principle of superposition, we'll just add all these three and we'll get our final moment diagram. How actually it is drawn? Now this is our simple cantilever beam with the UDL is acting 4K, right? Then what will be the moment? So if you see last slide, we have discussed all these things. So moment at this point, it will be, let's do it quickly here. So moment will be how much? So moment here it will be, so 4K, if 4K is acting at a distance of 10, so total how much force? 40 is acting. Total force is 40, which is acting at a distance of how much? If you replace this UDL into a concentrated load of 40, then this distance will be half simply, right? 5. So 40 into 5. So moment will be 40 into 5, it is 200. And what is the direction? Direction will be minus because it is clockwise direction, right? So if you draw the moment diagram for this beam, so this is the moment diagram. So up to this point it is 0, and then gradually your moment started, and when it reaches to here it is minus 200. That's what we computed, right? Minus 200 at this point. So now next one is this one. So this is a simple moment. I mean simple cantilever with a moment 300. So what will be its moment diagram? If you see, if you remember last slide we have discussed, this is simply a rectangular shape with minus 300. So this is the next one, and this is the last one. Is you have a cantilever beam with a point load. So point load means it will be, what will be the moment at this point? It will be 25 into 20. 25 into 20 is 500, right? So at this point you have the 500. So that's what 500 is written. So if you see, if you add now, so originally this beam was a hinge beam, right? So this is a hinge support. So hinge support means what is the moment? So moment should be equal to 0. So now let's superimpose all these moments. So how much we will get? So here moment is minus 200, here it is minus 300, and here it is plus 500. So what is the moment at this point? Net moment. Net moment here at this point is 0. So which is actually matching with our hinge support. So hinge support also here moment should be equal to 0, right? So after you superimpose all these three diagrams, diagram 1, diagram 3 beams, basically you will get 0, 0. Similarly at this point here at the middle you have minus 300, and you compute whatever you will get, and it will be something like, 200. So here I think it will come as 200. So 200 minus 300, so something you will get, and basically, so this is the net. If you add this diagram and these three diagrams, so this three diagram you will get, this is the final resultant diagram. So this is the moment diagram for this beam. Over. So that's simply we divided our entire beam into three parts, and we added these three part, and we simply added these three part, and we got our final figure. So this is our final figure. So this is very simple method of principle of superposition. Using the principle of superposition, actually we can compute the bending moment diagram very efficiently. So whatever whatever may be the load, maybe there may be a 1 unit point load, or maybe another UDL is acting, whatever may be there. So using that, simply break into multiple simple beams, simple cantilever or simply supported beams, and then we can easily draw the bending moment and shear force diagram of that complex beam. Thank you.